Okay, folks, this is a quick video for section 2.3. The first part of section 2.3 is very important. It develops the limit properties, but it can also be a little bit tedious. And in order to save some time in class, I thought I'd go ahead and create a video about it. So what we want to do here is develop some general properties so that once we learned how to compute a few limit values, we can go ahead and compute many others based upon these properties. So we're going to start off with this sequence of the basic limit laws. We're going to start off assuming that we know that for some function f of x, that if the limit as x approaches a of f of x is equal to m, and then for another function g of x, the same limit as x approaches a, the same limiting value, I guess I should say, is some number n. Well, what else can we do? Well, the first property says that the limit of the sums is the sum of the limits. That's the first property we want to give. What does that look like mathematically or written out in symbolic language? Well, this would say that the limit as x approaches a of the sum of these two functions can be determined by simply distributing the limit over the summation operation. So there's the summation operation. We're going to distribute the limit over that. So this would be equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. And just to sort of fill this out, since we said that this limit right here would evaluate to be m, then we can go ahead and replace that with an m and replace this expression here with an n. Now, something that's very important about these properties and kind of gets lost as we're developing them is that we already assumed that these underlying limits exist. We knew this existed. We knew this exists. And that was the same with both of these. So only because we knew both of those exist, then we were able to distribute the limit over the sums. So these properties do not work if, for instance, let's say this second limit, the limit as x approaches a of g of x, if that limit didn't exist, then we couldn't apply this property. Okay, so that's something that's easy to lose sight of as we go through. All right, here's the next property. It says that the limit of the product is the product of the limits. So mathematically or symbolically, what would that look like? Well, we'd say the limit as x approaches a of the product of these two functions, f of x times g of x, is equal to the limit as x approaches a of f of x times the limit as x approaches a of g of x. Well, we already knew that this limit here was m, and that this limit here, the second limit here, was n. So if we want to take the limit of the product of these two functions, it's just the product of the two limits. Okay? Again, let me reiterate that we already knew this limit existed, or we were able to show eventually that this limit exists as well as this one. So this property of distributing a limit over the operation of multiplication, that only holds if these underlying limits end up existing. At this point, let me just say, at this point, we're seeing that limits are very well behaved. They distribute over sums, they distribute over products. We're going to see here in just a minute, they also distribute over quotients. The limit of the quotient is the quotient of the limits. Folks, sorry, I got interrupted. The limit of the quotient is the quotient of the limits. Okay? So this says that if we look at the limit as x approaches a of f of x divided by g of x, how can we simplify this using these properties? So pause the video for a moment and take your best guess of how you would interpret this. The limit of the quotient is the quotient of the limits. So pause the video. So what we're saying here is we can distribute the limit over the quotient. That's as x approaches a divided by the limit as x approaches a of g of x. What did I do there? I distributed the limit to both the numerator and the denominator. Now, There's one caveat here. This will only apply as long as n, this particular limit, isn't 0. So we've got to add to this, provided the limit in the denominator isn't 0. Okay? So this is a very important point, because actually a lot of limit questions that we do in this class will be in the form of a quotient, and we can only distribute the limit to the numerator and the denominator provided the limit of the denominator doesn't come out to be 0. If n were 0, then this step right here, this distribution step, would have been an illegal step. So that's something important to keep in mind. The last property of the last main property of the limit laws that I want to give is really just an application of the product rule, but let's go ahead and state it like this. If we take the limit as x approaches a of some constant called c, just some number c, times f of x, what could we do? Well, it turns out that constants factor out of limits. So this would be c times the limit as x approaches a of f of x, which would be c times m. So we could say that constants factor out of limits. Okay. Folks, these four properties that we've given here, the sum rule, the product rule, the quotient rule, and then the constant factor rule, these four properties are ones that we're all just going to kind of take on faith. I will prove a couple of them for you when we get to section 2.7, but until then you can go ahead and just use them, okay, without justification. So those are the four limit laws.